On this slide, you may see the contents of what will be discussed today. In introduction, I will show you types of finite element models that are used in practice for connection design and analysis. Also, I will explain the benefits of connection detailed finite element modeling. Then I will show you approach to model bolted connection, contact between plates, how to model field welds, and how to calculate connection model in case of submodeling. And the last part will be about users' experience with Midas software for connection design and analysis. I'll show you several of them. If to talk about connection design and analysis with usage finite element method, several ways can be presented. The first way is commonly used and based on global finite element analysis of the whole structure. Here, global model is mostly created using beam or truss finite elements, and from this global model, engineer the text connection and member forces, and then perform design of connection using special design model or some external software. And this software usually includes formulas and safety criteria according to design code. Second and third ways are for detailed finite element analysis. This model is known as component-based finite element model, and here connection members are created with a shell element, and joining of these members like bolts, contact, welds are performed with special links elements. And this model is based on 3D solid finite elements. All parts of connections, like members, bolts, welds, are made of solid elements. And here also uses surface contact penalty method or interface elements for interaction. So using Midas software, it's possible to consider all these types of connections. Here I'd like to show you analysis cases where detailed simulation of steel connection is necessary or preferable. Sometimes during the design and detailing of frame or trusses, it's not obvious with what kind of connection you will come up, and as a result, joint system could have quite complex stress-deformed state, and analytical formulas do not predict corresponding strength capacity. So a detailed finite element simulation is necessary here. Then praying action and contact action estimation. Most design codes have formulas for considering this effect. However, design codes cover only common cases, only typical types of connections. But detailed finite element simulation can be used in general cases. Another example is gusset plates. This component is very important in connection as it transfers loads from one connection member to another. And gusset plate shape should be optimized according to cost efficiency and strength and buckling capacity of the at the same time. So here finite element simulation can describe a real buckling shape and of plate, and also can allows to consider plastic strain distribution. And the last example of usage detailed finite element modeling is design of retrofitting systems. This is necessary for structures that are under the service a long time, where the connection has some problem with the capacity, like reduction of thickness of plates due to the corrosion or because of fatigue or crack initiation. So for most design cases in terms of detailed connection analysis, this shell element model approach is widely used. A 3D solid model, of course, can describe connection behavior in more details. However, modeling and analysis with this type of modeling is it's time consuming. 3D solid model is mostly suitable for research investigation. So I'll focus on this type of connection modeling. The next part is about modeling of poles and contact between surfaces. Here you can see end plate connection, example and schematic description of finite element modeling. In this description, shell elements describe beam flanks, webs, and plates at general plates meet surfaces. This modeling bolt can be modeled with beam or an elastic link element, and contact between surfaces can be modeled with a compression-only links. If plates are compressed, the link stiffness doesn't allow deformation between plates, and separation of plates can be described by zero stiffness of links. On this slide, you can see a Midas FEA functionality to model described elements of connection. So for contact between surfaces in elements property in elastic link, you can define compression only type, and here you have to define stiffness for the spring. Because of your considering compression only, allowable tension should be 0, so only compression is allowed. And else, Midas FEA has special feature automatically generate links between nodes. So you have to select nodes of the first part and then select nodes of the second part, and this link will be generated automatically. As for the bolt connection, you have to apply here beam element, and you have to merge this beam element with separate surfaces using rigid links. In the properties for beam elements, you define stiffness of the bolt, and as for the rigid link, you have to define a rigid body type in properties. Now I'm going to show you a working example. In Midas FEA, I will demonstrate how to create this bolted connection in the Untitled Chapter model. Also, I will show you a comparison of results between shell and solid finite element model. This is a starting point of modeling. I have here already surfaces of connection. Here are the materials for plates and for future bolts. And here's the element properties for shell elements. These properties are for flanks, for web, and for plates. And here's a mesh generated for surfaces. So now I'm going to find here in this model bolted connection. So first of all, I will create properties. First property is for beam element for my bolt, bolt M60, and for section template, I'm selecting solid round, and diameter of the section is 0.060 millimeters. Next is in other properties, I will define a rigid link to merge my beam element with the separated plates. With a rigid body, I click apply, and in elastic link I will select compression only properties for contact between plates. Stiffness will have quite huge value, almost infinite value. at a low tension 0. Here's the name, will be contact. Okay, now I'm going to create both elements. So first of all, I need a node at the center of this hole. To have this node here, I will create a 3D line, and middle of this 3D line will be a center of a circle. So here's my node, and then I go to element, create link. Link type is a rigid link. Here is my master node. And these nodes are slave. Property rigid body, and I click OK. I'm going to copy these links to this hole. In the mesh, I'm selecting translate mesh. I'm selecting this element. Direction by 2-point vector. And distance between these two plates is 10 millimeters. Here is how it will be copied. I agree with this and I click OK. Now I'm going to create beam element between these two nodes. So I go to mesh, element, create element. Here's element type is linear and properties M60 for beam element. And click OK. So I can check this section. I can render this section. In the Preworks, I can click show section here, and I see it looks correctly. Now I'm going to copy all these elements to other holes. To do this, I go to mesh and translate mesh. I'm selecting these elements. Direction will be defined by 2-point vector. This is in transverse direction. And distance between center of these holes is 50 millimeters. Click apply. And in vertical direction. Okay, to be sure that all my nodes are merged, I can go to mesh, node, and merge. I'm selecting all the nodes, and here's a tolerance 1 millimeter. Now I'm going to define a contact spring between these separate surfaces. For this, I go to mesh, element, and here's a connection. The method is a closed link. I'm selecting nodes of the first part, and then I'm selecting nodes of the second part. Property contact, and I click OK. So here's my links automatically generated. I'm going to apply boundary conditional law to this connection. So As for the load, this connection will have bending, and to produce this bending between separated plates, I will apply here a fixed constraint, and at this end I will apply bending moment. To do this, I go to Analysis Boundary Conditions. In Constraints, I'm selecting these nodes. All degrees of freedom are fixed, and I click OK. To apply bending moment here, I have to apply this load at the center of gravity of this section. For this, I have to apply here rigid body. To have a master node at the center of this section, I will create here a 3D line, and middle of this 3D line will be my master node. I go to Mesh, Node, Create. Yeah, here's my master node. Now I go to Mesh, Element, and Create Link. This is my master node, and this node a slave. And OK. So now I apply bending moment. In Load, Force, I'm selecting this master nodes. In the moment, apply master node and apply bending moment about this axis, x-axis, and the values will be 20 kilonewton meters, and OK. So now I can perform the analysis. In analysis case, we have to define nonlinear static because we have nonlinear boundary conditions, compression only springs. In analysis control, you have to define material nonlinearity. A Newton-Raphson method for iteration is enough for this approach. And if you want to consider time history, if you want to consider a stress-deformed state of this connection, and at each iteration step, different iteration steps, you can define here several number of steps. I will consider just one step. And for this kind of modeling, nonlinear modeling, the displacement norm criteria is enough with this tolerance. Okay. Here I'm activating what modeling properties will be considered in analysis. Click OK, and I perform the analysis. Now I'm going to check the results. In post-works, first of all, I check my displacement. So here you can see separation of plates, where the tension zone, maximum tension zone. Here's the compression of plates. Here are the forces and balls. You can see here the tension force, and the upper balls also has some small tension. It can be explained if I will go to forces and compression only links. You can see that compression area is above the upper bolts, where the top flank of beams. Here is a Midas stress distribution in plates of connection members, and the maximum stress distribution is where the tension is on. Now, comparison with 3D solid model. On this slide, you can see a deformed view of model and end plate separation. The picture is similar, and vertical displacement in shell model is 2.6 millimeters, and in solid model 2.7 millimeters. Here is the Midas stress distribution in web of beam, and the average stress is 280 MPa. And on this slide you may see the contact area models. The contact area are above the top bolts and where the top flank of beams, so the picture is similar as well. The next part is about welds modeling. Here I'll show you how to consider filled welds in connection shell models and how to determine the strength in these welds. Here weld is modeled by shell elements, and shell arranged between a mid points of weld legs line, and these shell elements are connected with a mid surfaces of plate by rigid links and multi-point constraints. The thickness of the weld is equal to the theoretical weld throughout length. On this slide you may see a modeling approach in isometric view, and for the weld shell elements you may define nonlinear properties and consider its plastic deformations. The benefit of this approach is in establishing of limit state of welds. The equivalent stress that you can determine of the central weld shell element you can compare with the design limit stress. Also, if you consider plasticity of welds in the connection model, you can compare this plastic strain values in shell elements of welds with the limited strains proposed by design code. For example, according to the Euro code, this limit plastic strain can be taken as 5%. Now, how it can be modeled with a Midas FEA functionality. As for the rigid links, you can define rigid properties and then create link element between shells. And according to the multi-point constraint approach, the constraint node can be arranged at any place and not be merged directly with other nodes. And this constraint node inherits displacement from surrounding independent nodes. And in Midas FEA exists a linear constraint equation feature that allows to calculate average displacement from independent nodes and apply this displacement in this constraint node. But in Midas FEA also exists an alternative way to connect weld shells to plates with some simplification. At the beginning you create surfaces of connection components, then using imprint function you project weld shell edge onto the surfaces, and this allows you predefine identical fine element lengths along the lines and get nodes with rigid link at the same position in plates and welds. So now I'm going to show you the working example of this kind of model in Midas FEA, and I will consider plate to column welded connection with the described above principle, and also I will make comparison of results with a fully 3D solid model. This is my starting point of modeling, and here I have ready surfaces of my connection components. Here are the surfaces for welds, for attached plate and column. What I'm going to do first, I go to surface and imprint a surface. Here I'm selecting a shape where I would like to see a printed line. I'm selecting this edge and direction of imprint. Here's a preview of my imprinted line. I click apply. I do the same for the second color of the column flank. And I will imprint a line on this surface as well. Okay, next step, I'm going to create material and element properties. As for material, I will select one from database. As for the properties, I will define the thickness of shell elements. This one is for column flanks, column web, thickness of attached plate, and 7mm is for weld shells. I also will define here rigid link properties for links between shells. Now mesh size control. Here I'm selecting all my lines, and I will define the predefined length will be 20mm. So here's a preview of node arrangement along this line and edges of shell elements to weld. Now I can generate my mesh. First of all, I'm selecting weld shells, weld surfaces. Here's a property for the weld. Click apply. Now this plate. Flanks and web. Okay, now I'm going to add links between shell elements. So I go to mesh, element, create link. Here's my master node, this node as slave. And here two links as well. Now I can copy these links along the imprinted line. I go to mesh, translate, and select on these elements. Direction by 2-point vector. This length can be checked here. It's 90mm and 10 times. Here's a preview how it will be copied, so it looks okay. And I click OK. Now to be sure that all my nodes are merged, I go to Mesh, Node, and Merge. I'm selecting all my nodes and tolerance 1 millimeter. Okay, now I can apply boundary conditions and I can apply load. Here this column adherence will be fixed. I go to analysis boundary. I'm selecting these nodes fixed and apply. And then loads and force. Here will be applied axial load. To apply this load in the center of this hole, I will arrange here rigid link as well. And I will consider here axial load along the axis, 100 kilonewton. And okay, now I can perform the analysis. Analysis is done. Now let's check the results. So this is the formed shape of connection. And this is Midas stress distribution in plates. Now I'm going to compare the results with 3D solid model. On this slide you may see deflection contour imbalance in shell and solid models. Equivalent displacement is around 0.5 millimeters in both models. And on this slide you may see a Midas stress distribution in both shell and both throw and solid model. So the picture is quite similar as well. The next part is connection submodeling by predefined displacement. On this slide you may see the sequence of how to perform this analysis. First of all, you create your global model using PIM or truss elements. Here are the tools that you need for this kind of analysis. You apply dead loads, you apply moving loads, consider load combination, and perform member design. The next step is selecting of the connection you want to investigate in more detail. For this, you have to decide what are the dimensions of connection components will be included in detailed analysis. Also, you have to extract a node displacement adherence of the components. And the last step is detailed modeling of this connection. In this detailed model, you apply a predefined displacement, you make post-processing results. Now, I'm going to show you all these steps on the example. Working example is a welded truss railway bridge, and the purpose of detailed analysis is a use of plates in the main truss connection. This is a global model in Midas Civil. This model is created using beam elements. It has some material, some sections, some boundaries and loads. That place where I want to consider my connection, I approximated lowering and diagonals with many elements to get my nodes for displacement extraction. And by this way, I established dimensions my detailed shell model. This is already a model of connection in Midas FEA. It's totally generated with shell elements. And the ends of connection components are the rigid bodies. The master node position is the same as in a global model. In detailed model is necessary to keep node ID order the same as in a beam model. To define here a predefined displacement load, first of all, I go to Analysis, Load, and here I'm selecting Displacement Load. Now I'm going to select all my master nodes. And add some default displacement here. Then I go to Pre-Works menu, and where's my load displacement? I open table. And now in a global model, I'm selecting the same nodes here. I go to Results, Result Table, Displacement. Now I can copy all these displacement components and paste them here in this table. Now I can perform the analysis. And results. So here is a displacement of connection. To be sure that the displacement is correct, I can check this node value, 61.4 millimeters displacement. And in a global model, I can check results, displacement, and this value is also 61.4 millimeters. And now this allows me to investigate stress distribution in connection components. I can check Midas stress, and I can check concentration of stresses in the critical parts, like in a gusset plate. And by this way, I can play with the shape of my gusset plates. I can consider different load cases, different load combinations, and design a suitable shape. The last part about modeling of connection is submodeling using coupling links. This approach is suitable if you wish to consider at the same time detailed stress-deformed state of your connection and a global structure behavior. For this, for global deformation of the structure, it's enough to consider beam-fine elements or truss-fine elements in most cases. And inside this beam model, a detailed shell or solid model can be arranged. Links between these two different types of models achieved with rigid links or rigid bodies, similar to those I have used that I have considered in the previous example. And this rigid body allows to translate the beam element deformation from global model to the detailed fine element model, and this is possible because of beam deformation theory. Now I'd like to show you some of the users' examples where Midas software was used for connection design and analysis in terms of detailed shell and solid modeling. First example is about investigation of gusset plate, bracing system, and frame structure that is subjected to seismic action. Here was considered different shapes of gusset plates, and detailed shell model with nonlinear properties were used for this analysis. You may see strain distribution and connection, and you can see a clear line plate in case of brace and compression. And on the right is a brace and local buckling. This example is about reinforced concrete column connection to foundation using column shows and anchors. Column is subjected to time history seismic load. In this investigation, authors considered different finite element models of this connection and did comparison with experimental test. You can see a 3D solid model where all parts are made of solid finite elements, and contact interaction between parts was performed using interface elements. For the concrete was a total strain crack model was also used. On this slide, you may see a general view of experimental test, some results of experiment and analysis, and say a comparison. In this example was considered bolted lab connection using 3D solid model, but in this case bolt was simplified by beam element and rigid links. Author investigated the correspondence of this kind of modeling to design practice. In this example was investigated T-step connection based on experimental test and 3D solid model. Here was considered contact interaction with a friction and prey in action effect. And numerical results have good agreement with experiment, as you can see on the slide. And this is example of design project, a footbridge with cast steel nodes. Here connection was designed based on detailed shell and solid models that are connected to the global model via rigid coupling links. And by this way, a global deformation of the beam due to the pedestrian static and time history load was reflected on detailed stress-deformed state of connection.